Alright, next to last factoring video, what I'm going to show you is I'm going to show you how to factor the difference of perfect squares.
Factor binomials that are the differences of squares. Solve equations involving the difference of squares.
Alright, so what is a perfect square? Well, a perfect square is a rational number whose square root is a rational number. Examples of perfect squares are 25, because the square root of 25 is 5. That's the square root of 25 is 5. 36t squared is a perfect square because the square root of 36 is 6. So the square root of t squared is t. And 121 t squared is a perfect square because the square root of 121 is 11. And the square root of t to the fourth is t squared. Alright, remember when we learned that the product of binomials of the form, this was a sum and a difference, is the difference of their squares? Well, here's our key concept here is when we have two perfect squares and there's a difference between them, they factor into a sum or a difference. And it doesn't matter if you write quantity a plus b times quantity a minus b or quantity a minus b times quantity a plus b. So here's an example. So I have n squared minus 25. So we need to know, is this a difference of two squares? So n squared is equal to n times n. So that's a perfect square. 25 is equal to 5 times 5. So that's a perfect squared. So yes, it is because they have a minus sign between them. So they factor into the quantity n plus 5 times the quantity n minus 5. Another example, 36x squared minus 49y squared. Is this the difference of two squares? Well, it's definitely the difference because there's a minus sign between them. And look, 36 is a perfect squared, x squared is a perfect squared. 49 is a perfect square because it's 7 times 7. And y squared is a perfect square because it's y times y. So it factors into the quantity 6x plus 7y times the quantity 6x minus 7y. Alright, these are difference of two perfect squares. See if you can factor them. So pause the video, try it out for yourself, and restart when you're ready to check your work. Alright, here's what you should have got when you factored these. If you didn't, discuss it with me tomorrow. Alright, here's example 3. And if you look right here, actually, GCF, once again, we should always check for a GCF. And in this one, we have a GCF. 12 is a common factor of 48 and 12, and they both have a common factor of a. So when I factor that out, I'm left with 4a squared minus 1. So now I have two terms. Are they the difference of perfect squares? If they are, then I can factor them. And 4a squared is a perfect square. 4 is a perfect square, a squared is a perfect square, 1's a perfect square. So that means I can factor this quantity into 2a plus 1 times the quantity 2a minus 1. So here is the whole thing factored. Alright, here's another example. And I'm checking for a GCF. So yes, there is a GCF. I have a GCF of 2. When I factor, divide that GCF out, I'm left with x to the fourth minus 81. Now, since there's two terms, are those two terms perfect squares? If they are, I can factor it again. And yes, they are, because x to the fourth is equal to x squared times x squared, so it's a perfect square. And 81 is equal to 9 times 9, so it's a perfect square. So I can factor this into x squared plus 9 and x squared minus 9. And I'm not done there because x squared minus 9 is the difference of perfect squares once again, so I can factor it even further. Now, I can't factor x squared plus 9 because it's a sum, not a difference of two squares. But I can factor the x squared minus 9 into x plus 3 times x minus 3. And there it is, completely factored. Alright, so here's another problem. It's a big long one too. So first of all, as always, look for GCF. And you'll notice that all three of these terms have a common factor of 5. So I divide out 5 out of each factor, and this is what's left over. And now I look, I am factoring by grouping since I have 4 or more terms together. So these two share an x, and when I factor that out, divide it out, I'm left with x squared minus 1. And the same over here. So basically, here's what my problem looks like now. I have 5 times x squared minus 1 times the quantity x plus 3. But since x squared minus 1 is a difference of 2 squares, that means that I can factor that even further, which is 5x, and then the x squared minus 1 factors into x plus 1 times x minus 1, and I still have that x plus 3. So now I'm done. Alright, here's a couple, just as those last two examples, for you to try. Remember, look for GCF first, then look for difference of squares. So pause the video and give this a shot yourself. Alright, here's my answers. If you have some disagreement or some question, make sure you talk to me. Alright, here's a crazy looking problem. P squared minus 9 over 16. Now is this the difference of squares? Well, let's see. P is equal to P times P, so yep, that's perfect squares. And if you look, 9 is 3 times 3, and 16 is 4 times 4. So 9 over 16 also has to be a perfect square. So to factor these, basically, square root of the first plus square root of the second times square root of the first minus square root of the second. And since this equals 0, I can use my zero product property. So it's P plus 3/4 equals 0, and I subtract 3/4, so I get P equals negative 3/4, and P minus 3/4 equals 0, and I add 3/4, so I get P equals 3/4. So my two solutions are negative 3/4 and positive 3/4. Alright, so now we have an equal sign. So first of all, in solving this, we have to get it equal to 0 before we can solve it. So we do that by subtracting 50x from each side. Alright, these cancel out, and I'm left with 0 over here. I can't combine these two because they're not like terms. Now I've got to look for GCF, and I can tell you that they have an x in common, and I think they also have a 2. They're both even, so there's a 2. So when I divide out the 2, and you can do your factor trees and mark out whatever's in common to find your GCF if you're having trouble with that. And once I take out my GCF, what's left over is what I divide 18 by 9 is 18 by 2 is 9, and I took out one of my x's, so I have an x left. And then I take out divide 2 out of 50, which leaves me 25, and I take out an x. Oops, and that's an x squared. Alright, so now I have a 2x, and also 9's a perfect square, x squared's a perfect square, 25's a perfect square. So this is the difference of squares. So square root of first plus square root of second times square root of first minus square root of second equals 0. Now since I have an equal sign, zero product property comes into play, and I've got to take each factor, set it equal to 0, and I have got to solve each one of these equations to get my solutions. So I divide by 2, so one solution is x equals 0. So 0 is 1, two-step equation, negative 5, and then divide by 3. So negative 5/3 is another solution. Then on this one, I'm going to add 5, and 3x equals 5. I'm going to divide by 3. So x equals 5/3 is my other solution. Alright, try these two on your own. They're just like the last two examples, and when you've done and you're ready to check your work, restart and see if you got it right. So go ahead and pause the video now. Alright, so when you check your work here, this you just have to factor, and it's the difference of two squares, and you get the quantity q plus 2/5 times the quantity q minus 2/5. The second problem, you got to get it equal to 0, look for a GCF, factor it, set each factor equal to 0, and you get three solutions. Y equals 0, y equals negative 1/4, and y equals positive 1/4. Alright, and guess what? The end.